Let's take a look at an example where we use derivatives to measure rates of change in a particular context. So here the context is as follows. I have a table that gives the yearly annual income that a TIAA CREF investor can expect in retirement. So picture this scenario. You have a person who's contributing to a retirement plan, and they receive in the mail a statement that is designed to help them sort of get an idea of how their investments will grow and how much income that will provide to them when they retire. Let's say it's 30 years from now. So this mailer, this piece of information, has a table, and it says, for example, that if you can average a 3% annual return on your investments, your retirement investments, and you continue to contribute to them in a way that is similar to what you've been doing in the past, then when you retire, your first year income will be $32,900 per year. Now, if you can manage a 6% rate of return, then your first year income will jump to $55,500. And of course, as you can see, the higher the rate of return, the more you can get in first year income. So if you could manage 12% per year, which would be difficult, for most people at least, then your first year income is going to be quite high. So this is what the situation is that we're looking at. We basically have two variables. X is like the rate of return, and Y is like retirement income. And so we see that Y, retirement income, depends on X, the rate of return that we can achieve on average per year as we invest and prepare for retirement. So given that, let's take a look at what this would look like. What I've done here is I've modeled this data with an equation. I actually used Excel to do this. And I have a function I for income, that depends on P, the percentage rate that you earn per year in this retirement account. So I took this data, I put it into Excel, and I had it model an equation for me, or produce a quadratic equation for me. So P is the actual percent, so it's not a decimal. So for example, if you were going to get 3% annual income, the value of little p would be 3.0, not 0.03. So I've done that just to make the function a little bit easier to work with. And so what we want to do here is we want to discuss what the derivative of I actually tells you. Now remember, I is a measure of income retirement in the first year that depends on the percentage rate annual return. So what does the derivative tell you? Pause this video for a second and see if you can at least jot down your idea of what a good interpretation of I primed of P would be. And when you're done, pick up the dialogue and see if what you come up with is similar to what I say. Okay, so let's take a look at what I prime of P actually tells us. This is the rate of change of first year income, capital I, with respect to the interest rate, little p. In other words, it tells us how the first year income changes as the annual rate of return changes. A marginal interpretation would say something like this. If I could get 1 more percent per year, remember marginal change is always the change over 1 more unit. In this case, the unit is 1%. So if I could get 1 more percent per year over what I'm getting now, how would that raise my projection for my first year of income during retirement? So that's what the derivative of this function tells me. So let's take a look at the value of the derivative of the investment function at 10%, little p equals 10. The original function I is given here at the top, so the first step is to take the general derivative and then save the 10 for after we do that. So the general derivative is Pretty straightforward. We just take 2 times 1035, which gives me 2070, and then reduce the power of p squared down by 1 to just p. The middle term, 6366p, is a linear term, so the derivative is just the slope of that line, which is 6366. And of course, the constant term at the end has a derivative of 0. So this is the general derivative of the income function. You could call this the marginal income function that depends on the annual rate of return, little p. Now, to find out what's going on at 10%, we simply input 10 into the function and then do the calculations. So we get, as a final result, $27,066. Now, what does this mean? It's really important that we pay attention to not only the units, but how we interpret what this number actually means. So this tells us the following. If the investment is earning 10%, then if we can increase the annual rate by 1% to 11%, then our first year income, as a result, will increase by $27,066 per year over what we would get if we had stayed at 10%. So keep in mind, the $27,000 here is not the first year income. It's the amount of additional first year income we can achieve from eking out another 1% in the annual rate of return. Also, keep in mind that this number does not tell us how much income we actually have. If we wanted to know how much income we were getting, we would use the original income function. But what we're doing right here is we're trying to find out how the income changes as the rate of return changes. So you have to keep that in mind as you interpret these numbers. This final number of 27,000 roughly is not an income. It's an additional amount of income that we can get by making a small change to the variable little p. So here's a picture. You can see here the curve is the actual income function. It's part of a quadratic. Along the horizontal axis you have different percentage rates of annual return, and then along the vertical axis you have total income. So notice when p is equal to 10, then we're going to draw a tangent line at that particular point. And what this derivative tells me is that when p is equal to 10, the slope of this line is $27,066. And of course the units are dollars of first year income per additional 1% rate of return on the investment. So that